So in this video we'd like to talk about the concept of a power series and then what is known as the interval and radius of convergence. So first of all, what's a power series? A power series is a function defined by a rather special formula. In particular, something like this. So here f of x is a constant plus a constant times x minus a plus another constant times x minus a squared, and so forth and so on, forever and ever. In other words, it's a function which is defined pointwise by a series. The coefficients of this power series are c0, c1, c2, and so forth. We'll think of them as being real numbers. And here a is the center of the power series. So this is a power series centered at a with coefficients c0, c1, c2. We could also look at a power series that was centered at something, different thing like x naught, let's say. Then if it was centered at x naught, it would look like c0 plus c1 times x minus x naught plus c2 times x minus x naught squared, and so forth. So there's two different notations that are popular. The one is the plus dot 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 notation, like so, and the other is this so-called sigma notation. All right. Both have their place, and you need to learn both. So, of course, we've already been using the sigma notation in our study of series, numerical series, so far. So to give you an example of a power series, we could look at 1 plus x squared plus x cubed, and so forth and so on. This is a power series centered at 0. And you notice that we could use the geometric series result, right? To rewrite that as 1 over 1 minus x, not for all x, but for x that are within distance 1 of 0. All right. Anyway, in this case, you can see that the domain of the power series is minus 1 to 1, neither one of those included. And in fact, this is a Maclaurin series. What's a Maclaurin series? A Maclaurin series is a power series centered at 0. All right. So, to give you give another example, which is very much related to the first example, if we start with 1 over 1 minus x, right, and I do something kind of sneaky, what I'm going to do is I'm going to add 2 and subtract 1, because that's the same, right? If you work out 2 minus parentheses x plus 1, that's actually 1 minus x. Now, the reason I did that was so then I could factor out a 2, so factoring out a 2 leaves a 1. Minus 1/2 x plus 1. And if I do that, then I can use a geometric series result, identifying a as 1/2 and the ratio of the series is 1/2 of x plus 1. And so then I can expand this g of x as a power series centered at minus 1. All right, like so. And now I can only do that. Sorry, I'm still trying to make sure I'm not off the edge of the world here. So I can only do that for when the ratio of the geometric series, the r, is less than 1, which means then that 1/2 of x plus 1 has to be less than 1, which is to say that x plus 1 absolute value has to be less than 2. Puts you in this open interval between, with plus or minus 2 from minus 1. And so with all this in mind, I can define a new function, in fact a power series h of x, like that. I can say h of x equals to 1 over 2 to the n plus 1 times x plus 1 to the n. That's a power series. The domain of this power series is minus 3 to 1. And it's got a center at minus 1. Its coefficient is 1 over 2 to the n plus 1. And so this is kind of neat, right? This is also a power series that's got something to do with that 1 over 1 minus x function, right? But this one's centered at minus 1, whereas the previous one was a Maclaurin series. So there's a distinction, of course, between this 1 over 1 minus x function and the power series, right? The idea is basically this. This power series represents g of x close to minus 1. All right, and in contrast, example 1, this power series represents 1 over 1 minus x close to 0. let me just add something here real quick. If we draw a picture, we can kind of understand what's going on even now. And we'll look more at these ideas as we continue on. The idea of representing a function by power series is one of the big goals in this part of the course, understanding how we do that, when we can do it, what the limitations and so forth of that are. But if I just draw the graph of 1 over 1 minus x, what's that look like? Well, if you want, we could write that as 1 over minus 1 over x minus 1, right? Maybe that would allow you to clearly see it's got a vertical asymptote at 1, right? And let's see here. It's positive. It's positive back over here. And it's negative over here. Something like that, right? And so essentially what we just learned is that you can represent this expression, if we center it at 0, like this. And here we have 1 over 1 minus x equal to 1 plus x squared plus dot 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 dot. But we can't get past 1, right? On the other hand, if we expand this purple function, which I've graphed in red, if we expand it at, like I was saying down here, at minus 1, minus 1 is x naught, right? Then it has a the domain of the representation, the power series which represents it about minus 1, goes from minus 3 less than x less than 1, right? And so that says 1 over 1 minus x we can write as, I got to think for a second here. What's that look like? Goodness gracious. Well, the first term's a half, and then the radius was 1, plus 1/2 of 1/2 x plus 1, 1/8 x plus 1 squared plus dot 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 dot. This is a power series expansion of 1 over 1 minus x, which converges between 1 and minus 3 and represents the function. Sorry, I'm going to find my red marker again here. It's in here somewhere. My kids keep coming and messing with my markers. I don't need pink. Like that. Anyway, I have much more to say about how a function is represented by a power series and how we find the power series which represents a given function later on. At the moment, we're going to focus our attention on, given a power series, what can we say about its domain? All right, so I'll get back to that, but I thought I should just break here from the monotony of looking at IOC and ROC and just give you a kind of sense of what we're aiming at, which is namely to represent functions by power series. All right. Moving along here. So in both example 1 and example 2, I've lost my cover sheet now. Oh no. In both example 1 and example 2, right, we had domains that were given by an open interval of real numbers. In fact, these are all the open intervals of real numbers. You have the whole real line raised to plus or minus infinity, either including or excluding the endpoints. All right, and then you've got finite intervals, either including both endpoints, including the left endpoint, excluding the right endpoint, excluding the left endpoint, including the right endpoint, excluding both the left and right endpoints, your finite intervals. And finally, you're just singleton, your set containing one point. Of these, cases 1, 6 through 10 are all allowed as domains, possible domains for power series. It happens that these are not allowed as domains of power series. In fact, you can see these as domains of something a little more interesting called a series that appears in something called the Frobenius solution in differential equations, but that's later. All right, not this course. So anyway, there's a theorem, in short, that says that cases 1, 6, 7, 8, and 9 are the only possible domains for power series, and for each one of these there is a characteristic radius of convergence. If we have the whole real line as the domain for the power series, the radius is infinity. The finite intervals all have a radius which is just some number less than infinity, finite radius case. In all of those cases, the open interval of convergence just excludes the endpoints. It's x naught minus r to x naught plus r. Sometimes your instructor might ask you for the open interval of convergence just to be nice, believe it or not. And then finally, the singleton is a radius 0, and it's a really silly case. It means that the only x for which this converges is when you plug in x equals to x naught. So you just get, this is just 0, or could be just 1. So the series converges to C0 in that case, and only at that point. Anyway, this is the theorem. If we look at a power series, it has a domain which is described as above. Either the radius is 0, infinity, or it's a finite value. Them's your choices. So that means that the problem of finding the interval of convergence, all right, zoom in a bit because it's kind of tiny there. So we can find the interval of convergence as follows. This is my typical strategy. We'll use the ratio test to find an interval in which the series converges absolutely, usually minus a less than x less than a plus r. Now, if this is a finite interval, then we'll check endpoints. For convergence or divergence, this usually will entail an nth term test or an alternating series test. And then, step 3, using the theorem we discussed on the last page, we're done. All right. Now, this is not a comprehensive advice. Sometimes it'll be easier. Sometimes you'll need to think or do some algebra before applying these steps. Let's look at an example. Find the interval of convergence. Now, you'll have to forgive me for some of the numbers here. These are from notes I wrote originally for residential Calculus 2 here at Liberty a few years ago. But the numbering doesn't concern us. Anyway, example 3. So we have sum n equals 0 to infinity of square root of n times x to the n over 3 to the n. So I'm going to say this is the series at x. So I take the limit as n goes to infinity of a sub n plus 1 over a sub n. I get this. And then doing some algebra, I have x to the n plus 1 and x, which just leaves me an x here. And the 3 to the n plus 1 and 3 to the n simplify to 3. All right. And make sure. Yeah, you can still see what I'm doing. So I pull the x out, the absolute value of x out, because it's got no n dependence, right? And then this, well, that limits to 1, right? And so L from the ratio test is 1/3 the absolute value of x, which means that L is going to be less than 1 if 1/3 the absolute value of x is less than 1, which is to say that the absolute value of x is less than 3. So that tells me that the series converges on minus 3 to 3, right? So minus 3 to 3 would be the open interval of convergence here. So step 2 then is to check endpoints. So I got to check the endpoints I got to test for divergence at plus or minus, convergence or divergence at plus or minus 3. S of 3, plug in 3, that gives me root n. That diverges by the nth term test. When I plug in minus 3, I get minus 1 to the n root n, which again diverges by the nth term test. So in fact, the interval of convergence here was precisely minus 3 to 3. This example, first example. Next example, and sorry about this one, it's gotten awful fuzzy. I'm going to rewrite this one so you guys can see it better. So what we're looking at here is the sum, I believe, n equals 0 to infinity. Come on, work for me, pen. 2 to the n times x plus 1 to the n. All right. So this one, we don't need ratio test or anything. We can just look at this and go, wait a second. That's a geometric series with a equals to 1 and r is equal to 2 times x plus 1, right? and so it's going to converge if the ratio is less than 1, which gives me that the absolute value of x plus 1 is less than 1/2. So my radius is 1/2, and my interval of convergence is -3/2 less than x less than -1/2, which if we were to write in interval notation, it is -3/2 -1/2, right? That's interval notation, all right? So if I ask for interval notation, if your instructor asks for interval notation, they want that, okay? All right, next example here. And this was actually a test question from a previous Calculus 2. Previous Calculus 2 that I taught. All right. So consider f of x equals to 1 over n times x over 3 to the n minus 1. We're asked to find the IOC and ROC for this power series. So again, I start with the ratio test. And ratio test leads me to the absolute value of x over 3. If that's less than 1, that gives me that the L is less than 1. And so it tells me that the interval of convergence is -3 to 3. Again, I got to check the endpoints. So here, we check the endpoints. F of 3 is ends up being 1 over n, right? I hope you understand what I'm doing here. I'm plugging 3, so I put 3 in here. I've got 3 over 3 to the n minus 1, which just leaves me 1 over n. So that's why f of 3 is just the p equals 1 series. Likewise, when we plug in -3, we get -1 to the n minus 1 over times 1 over n, which is the alternating harmonic series, which we can prove converges by the alternating series test. So in this case, the IOC, it includes -3, but it excludes 3. All right. So again, the ratio test allows us to figure out what the open interval of convergence is, and then we got to check endpoints by other means. All right. Let's look at another example. Actually, the upcoming examples are from a previous edition of Stewart. I would imagine previous. Who knows what edition we're in at the moment, but this is from Stewart's 6th edition, and I think you'll find that the problems are very similar to the problems in your text anyway. So here we go. Find the IOC and ROC for f of x is equal to -1 to the n times x to the n over n plus 1. So what do I do? Ratio test. Apply the ratio test. What happens? I work it out, do the algebra, I get absolute value of x. Then, so that tells me if that's less than 1, I get convergence by the ratio test. So -1 to 1 is a subset of the interval of convergence. Next up, I check the endpoints. Plug in 1, I get the alternating harmonic series, which converges by the alternating series test. Plug in -1. This time I get those cancel, and I get 1 plus a half plus a third. That's no good. This is the p equals 1 series. That diverges. So, in summary, the interval of convergence this time is -1 to 1 included. And the radius of convergence is 1, right? So, if you take the distance from the right endpoint to the left endpoint, that would give you the diameter of the set, right? And then take the diameter, divide by 2, that's the radius. You can think of it that way if you like. I should say, be clear, you got to take the absolute value of the, the right minus the left should always be, I guess it could be negative. Anyway, you take the absolute value of the difference between the endpoints and your interval, that should give you the diameter. All right, next up. Find the IOC and ROC for root n times x to the n. All right, so again, first step, I apply the ratio test. So ratio test gives me n plus 1 over x to the n, square root of n plus 1 times x to the n plus 1 divided by the square root of n times x to the n. Do my ratio test, algebra, pull out the absolute value of x because it doesn't depend on n, and that gives me this, which, as n goes to infinity, that goes to 0, so we get square root of 1, which is 1, so we get absolute value of x. So again, we have radius of convergence, 1. We know that -1 to 1 is in the interval of convergence. The question is, are the endpoints included? check the endpoints, and this time both of them diverge by the nth term test. Huh. Maybe I did this example already. I don't know. I feel like I might have done this one already. My apologies if we got a rerun here. Maybe you didn't understand it the last time, so this time worked better. I don't know. All right, next up here. X to the n over 5 to the n times n to the 5th. That's kind of symmetrical, isn't it? Find the IOC and ROC. So you know what we're going to do? The ratio test. So we do the ratio test here. N plus 1, 5 to the n plus 1, n plus 1 to the 5th, times the reciprocal with n, x to the n over n to the 5th, 5 to the n. And you do your algebra, and out pops the absolute value of x over 5 in the limit. So if L is less than 1, that's going to be true if and only if. That means if and only if. That's shorthand for if and only if, which is also the meaning of this symbol right here. This means if and only if. Anyway, L being less than 1 is interchangeable with the absolute value of x over 5 being less than 1, which is to say that the absolute value of x is less than 5. So lo and behold, we have radius of convergence 5, and then we've got to check endpoints. So in this case, x equals to 5, I get converges by p equals 5 test. X equals minus 5, I can get converges by alternating series test, all right? And so in short, this time the interval of convergence includes both endpoints, minus 5 and 5. So I think we've seen every different variety now. We've got sometimes both endpoints are excluded, sometimes the left is included, the right's excluded, sometimes vice versa, right? So all 4 cases can happen and do happen. Which one it is, you don't know until you look at the details. Here's another one. Actually, I can tell you what happens ahead of time. We're going to find that the endpoints both are included, because at the endpoints this is a p equals 2 series, either alternating or not. All right, let's go through the details. Here's the details. First of all, ratio test. I do the algebra. I get the f's value of 4x plus 1 less than 1. And so then I study what that means. That means that minus 1 is less than 4x plus 1 is less than 1, which if we subtract 1 across this, we get minus 2 less than 4x less than 0. Divide by 4, minus 1/2 less than x less than 0. So apparently minus 1/2 to 0 is included in the interval of convergence. Now I check endpoints, and I get, again, they're both included by either p equals 2 or the alternating series test. And so the interval of convergence is minus 1/2 to 0, both included, and the radius of convergence is 1/4. So there you have it. You know, to see that the center of this series is minus 1/4, we could have done a little bit of algebra up here at the start. Now that wouldn't really helped us. It wouldn't have simplified. Wouldn't have simplified the things I just talked about, but maybe it'd be nice to see. So if I factor out a 4, right? If I factor out, I can factor out a 4 to the n over n squared, and then that would put an x plus 1/4 to the n, like that, right? So you can see that x naught equals to minus 1/4 if you repackage the given formula like that. So it's not surprising that we found something that was centered at minus 1/4, right? Of course, while I'm at it, I might as well mention that another way to do this would have been that 4x plus 1 is equal to the absolute value of 4 times x plus 1/4, right? Which is equal to 4 times the absolute value of x plus 1/4. Right, and we needed that was less than 1, so that gives us that the absolute value of x plus 1/4 is less than 1/4. And so that from that you can directly see that the center is minus 1/4, and that the radius is also 1/4. So I'm not discouraging the initial calculations. I'm just saying that they can also be understood in the green way. All right. Now, 30 is a little bit more symbolic, and that's good. It gives us a chance to think about the theorems here. So suppose we're given that the series converges when x equals to -4 and it diverges when x is equal to 6. What can we say about this series, this series, this series, and that series? Oh my goodness. So what you're looking at here is f of 1, this is f of 8, this is f of -3, and this is f of 9 if I label the given thing f of x, right? So let's call this thing f of x. I'm not sure if I was inside the, I'm not sure if I'm off the edge of the universe when I wrote that or not. Maybe I am. Oopsie. Sorry. Hope I haven't been talking off the, I better zoom back out a bit. Hopefully it's not too late. All right. Let's see here. All right, so again, if I call this f of x, this is f of 1, f of 8, f of -3, and f of 9. To answer these, we note that the given series is centered at 0. So convergence at x equals -4 means that it must be that -4 to 4 is included in the interval of convergence, right? This is certain. The convergence is certain in here. Now we don't know what happens. We don't know what happens at 4, right? We are given, I should say we are given convergence at -4, right? So that's included. This is, I just don't know what happens there. This one is included though, right? And we're also told that it diverges at 6, right? So certain divergence is, out here. And we don't know about -6. We know at 6 it diverges. At -6 it may converge or diverge. We don't know. We don't have enough information to decide that. But beyond there it has to diverge. All right. Between 4 and 6, and between -4 and -6, we just don't know. All right. So now as you look at the questions A, B, C, D, they're easy enough to answer. At A we get convergence because that's at 1. At B, we have divergence because that's at 8. At -3, we've got convergence because it's in the red. And at -9, we're again in the green certain divergence region. So all of these are based on the interval of the convergence theorem, which again says that the IOC is either the reals or a finite interval. So I have another example like this, which I'll let you read. And finally this one, but I think that the time in which I can talk about these things has come to a close. So I hope that helps you. Bye.